All right, chain rule. Chain rule. So far we have just our basic derivatives that are like polynomials, right? Then we have the product rule and the quotient rule, right? Depending on whether we're multiplying or dividing. Now we have the chain rule. It's all going to be fine. Are we writing bad things on the table? We're going to be, we're going to write positive things. We're going to think positive things. And this does say this is the most powerful and important rule when differentiating. Chain rule. Oh. So far we've learned several derivative formulas and rules. However, all of our problems only contain a singular x as the argument. Okay, do you understand what I say when I say the argument? Like the cosine of x, x is the argument. Right? It's your subject of it. Okay? So we're going to consider the following and see what they look with and without the chain rule. All right, so we have, without the chain rule, we might have something that's just f of x equals x squared plus 1. And we can totally take the derivative of that. And with the chain rule, we might see something like f of x is equal to cosine of x squared plus 1. Where instead of squaring x, we're squaring the cosine of x, right? Which really, the correct way to write this is cosine squared x plus 1, right? Remember that? That's what that means. So, but when we're doing the chain rule and we're taking derivatives, we want to take it out of this form, which is most likely how it's going to be given to us, and put it into this form so that we can do the chain rule correctly. Right? So like this is the proper way to write it, but it's kind of like taking the square root of x and putting it as x to the 1/2 so we can have something to work with better. All right, so then we have the sine of x. We know how to take the derivative of that, right? But if I have f of x equals the sine of e to the x, then my argument is no longer x, it's e to the x. Okay, and that's going to require a chain rule. So make a little chain, so we go through. I have f of x equals e to the x plus the natural log of x. I could have f of x equals e to the x squared plus 1 power plus the natural log of the sine of x. So where I would have two chains here, because I have two terms, but I could do these separately, right? But then both of these, the argument isn't just x anymore. It's either x squared plus 1 or the sine of x. And then I have the square root of x. I can have f of x equals the square root of 1 plus x squared. So that's kind of how it looks differently. You have a function within a function, which would be like a composition of functions. Right? Where here, let's talk about how these all work here. That this is, well, if I made this right here, cosine of x would be like g of x, then this would actually be f of g of x. And this would be sine of e to the x, so it could be like f of g of x again here. It's a composition of functions. We've composed functions before. We'll look at how to separate that out in just a minute. So we're going to revisit the meaning of the derivative and what we're doing in some notation, okay? So it says consider dy dx. What does it mean to write dy dx? What about dx dt or du dy? That sort of thing. We're just talking about how we're taking the derivative. So it says find dy dt. So what this is really saying is we're taking the derivative of y with respect to t. So if I'm going to take the derivative of this whole thing right here, I'm going to write d over, and t is my argument, right? dt. And the whole thing is going to be y equals 2t cubed plus 4. Now, we don't always write that step. That's fine. I'm going to write it. And so what this is saying is I'm going to take the derivative with respect to t. So when I do that, the derivative with respect to t for y, this just gives me dy dt. And then if I'm going to take the derivative with respect to t of something with t's in it, then I just literally take the derivative, and this will just give me 6t squared. Okay? Does that make sense? That's really just more about notation. Like, what are we doing here? I I can't find dy dx here. Well, I could. I mean, I guess I could, but I don't have any x's, so that's not what makes sense. I'm taking the derivative of y with respect to t. So I'm taking the derivative of the function with respect to t. My function happens to be called y, right? So here it says find dy dx and dx dt. So it would make most sense that here, I'm just going to take the derivative of both of them. So the derivative, and I'm going to take it with respect to x on the first one, because that's what the variables that I have. So it gives me y equals 3x to the fourth minus 2x. So I'm taking the derivative of that whole thing. The derivative of y with respect to x is dy dx. And then when I'm going to take the derivative of this with respect to x, that means I'm actually taking the derivative with x there, and that's going to equal 12x cubed minus 2. Okay, so we're just revisiting notation. Like, this isn't new. That should hopefully make sense how all that flows. We good? And then I'm going to take the derivative of the second one. With this, x equals t squared, so I'm going to take this with respect to t. Okay, and that's x equals t squared minus 3. So when I do that, I'm taking the derivative with respect to t of x, so that's dx dt. And when I'm taking it with respect to t of this, that just gives me 2t. The derivative of negative 3 is 0. Okay, so that's just kind of revisiting some notation. We good? So here's how the chain rule works, and here's where the candy would come in if I actually had it today, but I don't. I might have it tomorrow. It depends on how long I make it here and if I make it home without collapsing first. But when I think of it as a Tootsie Roll Pop, you know what a Tootsie Roll Pop is? It's got the candy on the outside and the Tootsie Roll on the inside. Okay, you can't get to the Tootsie Roll part until you get through the hard candy outside, right? Whether you eat it or not, you got to get rid of it first, right? So you have to take care of the outside before you get to the inside, and that's what's happening here. So if we have y equals f of g of x, okay, then when I take the derivative, dy dx, I take the derivative of the outside and leave the inside alone, right? I'm eating that hard candy outside there, leave the inside alone. Then I take care of the inside once I get there. Okay, there's another way to look at it with u's and not looking at it as a composition of functions. We're going to kind of look at it both ways. You can decide on what makes the most sense to you. But this is for composite functions. I'm going to make sure you know what a composite function is here in just a minute. And that's when we're always looking for stuff, whatever your stuff is, inside the parentheses. It's not technically always in parentheses, because if we look back up here, this right here is not inside parentheses, but it's the stuff that isn't just x anymore. Does that make sense to you? So it's not, even though we're looking for, and this isn't technically in parentheses, but you know what I mean by that, right? That make sense? Good. All right. And the most important thing to remember for this is we still only take one derivative at a time. One derivative at a time. Don't do two things at once. Okay? That's just like when we're doing the product rule. The derivative of the first times the second plus the first times the derivative of the second. Only one derivative at a time. And outside first, leaving the inside the same, then multiply by the derivative of the inside. That's what's happening there. We're going to look at it as f of g of x. We're also going to look at it with these u's and du thing right here. I don't want to spend too much more time on that because I know that just looks like gibberish to you right now, but it'll make more sense in just a minute. All right. So here are our guidelines, which these guidelines, they're good to have and good to read, but I know sometimes it just looks like it's just a lot, and it's really not as bad as it looks. We want to rewrite. We always want to start by rewriting. Maybe all functions that need to be rewritten, but you want to make sure you have no radicals or variables in the denominator, okay? Unless using a quotient rule. Which means if you have variables in the denominator, if I have an x in the denominator, I want to rewrite it as x to the negative 1 power and pull it out of the denominator. Make sense? That's how we get it out. We don't just magically plop it up there, right? Identify the stuff inside the parentheses, which may or may not be parentheses, and set that equal to u. Okay. Again, we're going to do this two different ways. I think the u way is going to make the most sense to you in the end, but I want you to see the composition as well. We're going to write the functions in terms of u using the substitution above, differentiate using the chain rule, outside functions derivative, leave the inside unchanged, multiply by the derivative of the inside, write the final answer. Watch out for y equals e to the u power. With exponential, the exponent is always u. What's the derivative of e to the u? E to the u. It's easy. And that one gets a little weird because it's easy, right? But the derivative of e to the x is e to the x. The second derivative is e to the x. And because it's easy, it gets weird sometimes, but that's how it works, okay? So we're actually going to start, just because of the variables and what they use to name these, we're going to start with this second one, and we're going to do it two different ways. So you can kind of split your paper right there. And we're going to rewrite. So this is really technically still example 4, but I'm going to do it differently than what they're asking me for over here. And instead of writing f of x, I'm going to write f of g of x. F of g of x equals this right here, 3x minus 2x squared quantity cubed. Okay. So we're going to call that f of g of x. That's how it's a composition of functions. So we're looking for stuff inside the parentheses, and when there's parentheses there, it does actually help and make it a little bit easier. So we've got these parentheses. This is the stuff on the inside. Okay. So if we're going to decompose this, this is f of g of x, and I want to take it apart. G of x is inside here, and it's inside here. So I'm going to say that means that g of x is equal to 3x minus 2x squared, which means f of x itself would equal to x cubed. I want you to think about that for just a second. And if I gave you the pink ones and asked you for f of g of x, do you see how you would get what I have in purple there? If I want f of 1, don't I just take 1 and substitute everywhere I see an x, right? So I don't want f of 1. I want f of g of x. So I take g of x, I put it in there everywhere I see an x, and then I end up here, right? So that's how we got two functions. This function ends up inside of that function right there. Okay? So that's how the decomposing part of that works. And then our chain rule said that if I want f prime of g of, wait, actually, how does it work? Oh. If I say that, let me say that differently. That's why we revisited the y and stuff. If I have y equals f of g of x, okay? Y equals f of g of x, then dy dx equals, and this is the rule, you take the derivative of the outside, f prime of g of x, and you multiply it by the derivative of the inside, which is just going to be g prime of x. You see how that works with the decomposing part of that? And then we can go and find these things, okay, and go from there. Now, this same process without all the f's and g's and whatnot, we can use with the u's, all right? And so just know that u is always like part of a function here. So let's do it this way first. Let's do it instead of writing all that out, which you can if you want to separate them out and make sure you see them, or you can look at it this way. I'm looking for f of x, okay? It's going to be, but we're using what's called u substitution, and I'm going to take the inside part here that is my g of x, and that becomes my u. So that is my 3x minus 2x squared. Okay? I'm not saying you have to do both of these. I'm saying that's how it works as far as function notation and how to put one inside the other. The u substitution, which is a new concept, but really not going to be that bad. If this is u, then u prime, the derivative of this with respect to x, is going to give me what? What's the derivative of 3x? 3 minus, what's the derivative of this? 4x, okay? Then it says to rewrite f of x, okay? So we let u equal this part right here. So f of x is equal to now u cubed. Does that make sense why that is? If this whole thing is u, then f of x is now u cubed, because that's the u part that I took out of it. Okay, we good with that? So here's how the chain rule works. The chain rule says that if I want f prime, let's use dy dx is what I want. So dy dx equals f prime of u times u prime. And that's just a little easier than all the f's of g of x's, right? It's just kind of streamlines that. So f prime of u, this is f of x. F prime of u is the derivative of this right here with respect to u. What's the derivative of u cubed? 3u squared. Okay. So 3u squared, that's the f prime of u part, right? Times u prime, I found u prime right here. That's 3 minus 4x, and I have something with more than one term, so I'm putting it in parentheses. Ask me a question at this point. We good? Now, in the end, I can't have any u's left, so I know what u is. U is this right here. So this is equal to 3 times 3x minus 2x squared times 3 minus 4x. Okay? Any questions about where anything came from? This 3 right here, it came from this, which is the derivative of this. And so then I just went in and I substituted in for u squared, and he just kind of was along for the ride. Okay, good question. What else you got? Okay. It gets better, I promise. But this is another one of those things that takes some practice. So we're going to do the whole u thing again. We're going to do a couple without doing all that too, just to make sure that we understand what's going on here. Now, let's go back up to example 3. It says let g of x equal this right here. Now remember, we don't want to leave anything in the denominator unless we're doing quotient rule. Okay, and could we do quotient rule here? Yes, but do we need to? No, we do not. Because we can make this be g of x equals -7 times 2x minus 3 to what power? What power would have to go on those parentheses? How do I just magically get it out of the denominator? -2. Good, because there's no magic, it's math, right? -2. So for this, when we're looking for u, we look for stuff inside the parentheses. This is going to be our u, right? So u is 2x minus 3. U prime would be what? 2. Okay. So then I have to rewrite g of x. I just took this out and called it u. So this is now -7 times u to the -2 power. Everybody good with all that so far? So our rule is for dy dx, it's going to be f prime, oh, this is g. Maybe I should use g. G prime of u times u prime. Okay. So g prime of u, this right here, how do I take the derivative of that? What's that going to be? Good. 14 times u to the -3 power times u prime, which is 2. Any questions about where anything came from? Okay. Equals. Now, I need to substitute u back in here, and since that's to the -3 power, it's going to end up in the denominator, right? So I can go ahead and say 14 times 2, I know that's 28. Then in the denominator, I'm going to have something to the third power. That something is u, which is 2x minus 3. What questions you got? You have to get rid of the u's. You have to have all x's back, yeah. So you do have to go one more step, yes. But we're not necessarily going to have to use the u's in everything. I think maybe at the beginning it's probably better that you do, just so that you don't lose track of things. But here's how we could also have just looked at this. The chain rule is this, okay? Now I do want to rewrite it as this, okay? But so I rewrote it like this, right? So if I want to find g prime of x, I'm just going to talk you through it another way. And some people might latch onto this real quick. Others of you may be like, nope, still going to write out the u and the u prime for now. And that's totally fine too. It's the derivative of the outside, leave the inside alone, times the derivative of the inside, right? So if I take the derivative of the outside right here, okay, I'm leaving the green part underlined alone. That's going to give me 2 times negative 7, which is that 14, times 2x minus 3, I leave that alone, and then to the negative 3 power, times the derivative of the inside. The derivative of the inside there is just 2. And then do you see how I get the same thing? It's just 28 over 2x minus 3 to the third power. And there's less steps there, but at the beginning, because you have all these rules, and they might be a little confusing, it might be better for you to write some extra things. Okay, but you can kind of decide where you are and what you feel about that. But we're going to do a couple more together, and then I'm going to let you do some and see kind of where you struggle through on this. Okay? What questions do you have right now? All right, so now let's look at these derivative rules here. Now let's first just pretend like there were no u's here, they were just all x's. Okay? Now don't scribble out anything that I'm about to scribble out. Okay? But if we pretend like they're all x's and no u's, then we know that the derivative of the sine of u is the cosine of u, right? The derivative of the cosine of u is negative sine of u. Don't scribble those out. Tangent, derivative of tangent is secant squared. The derivative of secant squared, secant tangent, right? We know all of those things, yes? So what this is saying is, if u isn't just a plain old x, u is x squared or something else, then that's when you still take the derivative, but notice every time you just leave the inside alone. You leave the argument alone. So the derivative of a sine of x to the millionth power, right, is going to be the first thing you write is cosine of x to the millionth power, and then you take the derivative of what's on the inside. So the argument stays the same every time, then you take the derivative of the outside. Or the inside, rather, every single time. Okay, so just remind yourself, especially with the trig ones, that you're leaving that stuff alone. Okay, so you need page 2. So like I said, don't worry, there's more examples. We need more examples than just 2, I know. I'm not talking to you. Okay. So this one, I want this to go on the same page, which was what, 41? Yeah. 41. Okay, so we're going to start off doing the u and the u prime stuff, just like we have before. And so I have the sine, I don't have the sine of x, I have the sine of 4x minus 1, right? So this is the inside stuff. That's my u. 4x minus 1 times u prime, I'm sorry, not times. Then I need to find u prime, which is just 4, right? Okay, so rewrite g of x. That would be the sine of u. So since that's a u and not an x, it's not just going to be cosine of x, right? When I do this and I get dy dx, that is going to give me the derivative of the sine is what? Cosine. So I get cosine of u, that does not change, times the u prime, we'll just write that down just like that, times u prime, which looks just like that, right? The derivative of the outside times the derivative of the inside. Then we can substitute. The cosine of u is going to be the cosine of 4x minus 1 times u prime, which is 4. You can leave it like that, but you would most likely see it as 4 times the cosine of 4x minus 1. We all good with that? Any questions about where it came from? All right. Do I need to rewrite number 6 before I do it? Yes. Why? I have square roots in the denominator, and I have variables in the denominator, right? All right. So I do want to rewrite it because I have a square root and variables in the denominator, right? So this is going to give me, I'm just going to rewrite it up here so I'm more room. F of x is equal to, so it's going to be 4 times x squared plus 3 to what power? Negative 1/2. Great. Okay. All right. So what do you think u is here? X squared plus 3. Do we all agree with that and understand how to figure that out? Okay. X squared plus 3. If not, speak now, please. Okay. Then can we take u prime pretty easily? What's that? 2x. Okay. So then I want to rewrite f of x. This is going to be 4 times what? U to the negative 1/2 power. Okay. Everybody good with all that? Beautiful. All right, so then we're going to do dy dx. Oh, dy dx, if I can write an x. So this is going to be the derivative of the outside. So I go ahead and take the derivative of f of x, right? So negative 1/2 times 4 is what? Negative 2 times u to the what? Negative 3/2 power. Good. Times what? 2x, good. And you could write u prime or 2x there, whatever makes the most sense to you, right? Just in the end, all of the u's have to be gone, okay? So then this is going to be negative 4. Can I do that? Yes? If I get 2 times negative 2, can I multiply those? Get negative 4? Yes. Negative 4 times, I think x still goes in the numerator, right? Then the denominator, I'm going to have u to the, is that going to be cube root of u squared or square root of u cubed? Square root of u cubed. Okay, so square root of u, which is x squared plus 3 cubed. And I sort of clean that all up at once. If you need to take more than one step there, you can totally do that. Okay. What questions you got? All right, I'm going to give you a minute. Well, actually, bless you. Bless you. Yeah, y'all go ahead and try number 7. We'll talk through it together, but I want you to try it. All right, are we ready to work through this? Carolina, you should have paused this and worked this out on your own. Okay. Carolina's going to be the only one, she's the only one not here, so she should be watching the video. We'll see if she actually watched it. She'll know if I said her name or not. All right, so what do we think u is? Okay, good. 2 minus 5x. So then u prime would be negative 5. Beautiful. All right, so then f of x I would rewrite as e to the u power. Good. So then my dy dx is going to be f prime of x, right? So I take the derivative of this, which is what? E to the u, times u prime, which is negative 5, right? Then I got to get rid of all the u's. So this is going to be, I'm going to put negative 5 out in front. So it's going to be negative 5e to the 2 minus 5x power. So were you right, Ron? Yeah. But it seemed weird, right? The E1s seem weird because a lot of times they are way easier. They don't always look easier. They look a little intimidating, but they're usually easy which does cause you to second guess things sometimes, right? All right, so let's look at number 8. Actually, can you do number 8? Yep. All right, I got confidence back there. I'm giving y'all time to do number 8. Okay, are we ready to look at this one? No. What do we think U is? Good. There was a little pause there, maybe a little concern, but yes, we'll go with that. All right, so then the derivative of that's pretty easy, right? 8x minus 5? Yes. If I want to rewrite g of x, that's now going to be the natural log of u, right? Okay. And I heard some of you using your notes back there, which was very good, and having a little discussion about that. So dy dx, okay, I'm going to take the derivative of this. So what's the derivative of the natural log? 1 over x, so this is 1 over u. It's 1 over whatever we're taking the natural log of, times u prime, right? Okay, which sometimes I write that, sometimes I write that. It doesn't really matter at this point. But what you can do, what it does show you on the other side, that's one reason why I'm writing it like this, is it does show you end up with u prime over u, basically. It's okay if you didn't write that step in there right there, but that's what's happening. And so my u prime is 8x minus 5 over u, which is 4x squared minus 5x plus 7. Then I heard the comment of, I feel like maybe you could simplify this, okay? If we could, do we have to? No. Okay. If this is in the middle of something, might it help us if we could? Like, yeah, sometimes simplifying things can, but we can't simplify it, so that's fine, but that's good that, you know, maybe we need to, if we're done, we're done. But if we needed to move on, maybe something would cancel out, we could check, but we don't need to check. Okay? We okay with all that? All right, perfect. All right, so let's look at example 9. Okay, you go ahead and do that one. Oh, just calm yourself down. It's not that bad. This huge packet. All right, so I'm going to do this one without the U's and stuff. Okay? I know, I'm going to get fancy here. Because I just want you to think about this. It's the derivative of the outside, leave the inside alone, times the derivative of the inside, right? So the derivative of the outside, leave the inside alone, is f prime of x cubed, times the derivative of the inside, which is 3x squared. And that's pretty much what it is. If you put 3x squared times f prime of x cubed, that's fine. But that's the answer. Okay? So if you did all the U stuff, that's fine. I just want to show you that you don't have to. On what I just gave you, we're going to spend a few days on this, okay? Obviously, we're not even finished with these notes. But the front of what I gave you, you should be able to do all of that. The first part just asks you for U and U prime. Don't look at me like that. The second part of that is basically what we've done. We'll get to the rest of it, okay? But practice. This takes practice.